Okay, types of aqueous solutions and solubility. So let's think about salt water and sugar water. So salt water is a homogeneous mixture, a solution of sodium chloride and water. Sugar water is a homogeneous mixture of sucrose and water. You stir either of these into the water, they seem to disappear. We just talked about how we can measure the concentrations. What exactly, though, is happening to the salt and the sugar when we mix them with water? When we put a solid solute in a liquid solvent, there's competition between attractive forces. We haven't talked yet about what these attractive forces are, but there are attractive forces. So there are attractive forces between the solute particles. That's why it's a solid in the first place. A solid has the particles touchingly close and not moving relative to each other. If there were no attractions between those particles, they would be a gas at room temperature. So there are attractions here. There are also attractions between the solvent molecules. Why does water stay in the cup? Why doesn't it just float away and float apart? Well, gravity helps, but it sticks together because the water molecules are attracted to each other. So that's the solvent-solvent interactions. And then there will also be some attractions between the solvent molecules and the solute particles. So in order for this solid to dissolve, we need to break the interactions that are holding it together as a solid, and those interactions have to be replaced with the interactions with the solvent. So I think of this a little bit as like, here's this little group of girls, and they're all sticking together because they're out in the woods and it's scary, right? And everything's scary, and we're like each other, we're going to stay together. And then some, I don't know, maybe these are nice ogres. Here's Shrek. Shrek is green, right? Shrek comes up and he's all nice and everything, because this is after the first movie, not before, when he was really mean. So, here he is, and he's being nice to these little girls. And then they're willing to go off with him, and they're going to, mix thoroughly. If he was hateful, they'd stay together because there would be repulsion instead of attraction. If the water molecules or the solvent molecules are too stuck on each other, they will exclude the solvent and not let it in. Any questions about that?
Can you repeat what you said? Yeah,
So you can go to YouTube and watch it again. I don't know what I just said. So I think we're going to get to, you mean about the solvent molecules excluding?
Yeah, you said something.
So the solvent molecules, I think we'll get to this in a minute, but you know that water and oil don't mix, right? The reason water and oil don't mix is that water molecules are really attracted to each other. They're like, one of those cliques in high school. These people are just stuck on themselves. You want to get in and be a friend, and they're just like, nah, we don't have any time for you, right? And so they push people away. Water molecules are like that. You have to be just the right kind of solute to be able to get into the water. Oil is not the right kind. So the water molecules stick together. Their attractions are so great that they push the oil molecules out. And hopefully that'll, as we talk about the different things, that'll be a little more clear. So why do water molecules stick to each other? This has to do with the fact that there's an uneven distribution of electrons within the water molecule. So a water molecule is a molecular substance, oxygen and two hydrogens, and they are bonded with covalent bonds, meaning the electrons are shared between the hydrogen and the oxygen. Sharing is awesome, but sharing is not always exactly fair, right? You can share a bed with someone, but they've got like 3/4 of it and you're overhanging on the edge, right? And it happens every night. I don't know anybody that does that. It's sharing, but it's not equal. So the electrons that are being shared between these two atoms are not equally shared. The oxygen hogs the electrons. And so the oxygen end of the water molecule is a little more negative than the hydrogen end of the water molecule, because it's, I mean, we shouldn't talk about the bed, we should talk about the blankets. So the electrons are the blankets, and oxygen is hogging the blankets. Yeah, we're sharing, but hydrogen only gets a little corner of the blanket, and oxygen is getting most of the blanket. So this end is slightly negative, and this end is slightly positive. This happens in all water molecules. So here's our water molecule. This delta, by the way, that's a lowercase Greek delta. It means difference, generally. And here what it means is that you have a partial negative charge. This isn't an ion with a -1 charge. This is a fraction of a -1 charge, maybe a third or a quarter, a small amount. So here's this water molecule. And we're going to put some sodium chloride in the water. Sodium chloride is an ionic compound. It has sodium ions and chloride ions. Sodium ions have a positive charge. The negative end of the water molecule is attracted to the sodium ion. The positive end of the water molecule is attracted to the chloride ion. And so we have good interactions between the solute, and the solvent particles. And so the sodium chloride will dissolve because it can interact with the water molecules. So we see that each of these ions gets surrounded by a cluster of water molecules. The sodium ion has a +1 charge. It's going to take several water molecules coming around it with the negative ends pointed towards it to kind of balance out that charge and enable the sodium ion to leave the sodium chloride crystal. And the chloride has a -1 charge. It's going to take several water molecules with their positive ends towards this negative ion to overcome the attraction between the plus and minus ions. So what we end up with now is ions that are able to float around in the water. They're basically being escorted by water molecules, but they can move around freely, and they form a homogeneous mixture, a solution.
Is that what happens with like mineralized water and stuff? How they add minerals, but the water molecules like surround it?
Yeah, so water that contains minerals, minerals are ionic compounds, and so this will happen with the ions in those compounds. And so, you know, I've had questions about, well, is the deionized water safe to drink? No, it is not. Not because DI water itself is dangerous, but because of the nature of the system that we have in this building. Yeah, it's iffy. So I wouldn't drink that. What if you had distilled water that you bought at the store? Okay, that's also deionized because when you distill it, all you've got there, in theory, is pure water. Is it safe to drink that? Sure, it's not going to kill you. Now, is it healthy to drink that all the time? I would say probably not. Because tap water, groundwater, has dissolved minerals in it. Your body needs some of those minerals. And if you're always drinking distilled water, you're not going to get those trace minerals from the water. But yeah, mineralized water has the minerals dissolved in there. And those give a taste to the water. You know, some people are real connoisseurs of water. I'm not that picky, but some water doesn't taste very good, right? There's some cities around here, and it's like, wow, there's a lot of sulfur in there. It's like, ugh, right? I think that Fresno City water tastes actually pretty good. Tap water is good. But it's those dissolved ionic compounds that cause water to taste different. Any other questions about this? Electrolytes. You probably heard of electrolytes. You know that if you're exercising vigorously in the heat for a long period of time, you need to replenish your electrolytes, right? They tell you this on TV. Electrolytes are substances that dissolve in water, and when they do that, they form a solution that will conduct electricity. So basically, electrolytes are soluble ionic compounds. Because in order to conduct electricity, we have to have ions. Electricity is the movement of electrical charge, the movement of electrons. For water to conduct electricity, there has to be ions in here that can move the charge from one electrode to the next. So if we put salt into some water. Here we have a light bulb hooked up to a battery. The light bulb will light up even though these two electrodes are not touching each other, because the salty water can conduct the electricity. Salt, table salt, is an electrolyte. If you put sugar in water, the light bulb will not light up. Sugar is a molecular compound. It does not form ions in water, and so there's nothing to conduct the electricity. So that's called a non-electrolyte. They dissolve, but they don't conduct electricity. Most molecular compounds are non-electrolytes. Does this mean that water and electricity are fine and you don't need to be careful around, if you're standing in a puddle using electrical tools? Does this mean it's okay to be out on the water during an electrical storm because water can't conduct electricity? No. Is the water puddle that you're standing in the, the backyard, is that pure water? No. It's probably a lot dirtier than the tap water, right? Because it's on the patio, and who knows, the dog peed there, there's all kinds of stuff in it. That will conduct electricity pretty well, and so that's why you really need to be careful with electricity and water. If you were standing in pure water, a moderate voltage would not cause a problem. Lightning is going to be a problem regardless, because lightning is just a tremendous amount of electricity. Did you guys see the thunder and lightning last night? It was pretty impressive. It's fun. I grew up in the Midwest, and we had storms like that several times a week in the summer. And that was, it was a big one for here, but compared to what we see in Minnesota, it's nothing. We still enjoyed it, though. So let's look what happens when sugar dissolves in water. So a sugar molecule also has some uneven charge distribution because the oxygen and hydrogen, they never share equally. And so the negative end of water molecules is attracted to the more positive atoms in the sugar molecule, but it doesn't form any ions. It does get surrounded by water molecules, which lure it away from the other sugar molecules. They feel comfortable, so they're willing to go off with the water molecules. It will dissolve. In fact, it dissolves very well in water. You can put a lot of sugar in a solution of water, but it doesn't form ions. We've talked a little bit about acids. We learned how to name them and write their formulas. We used this description earlier. Acids are molecular compounds that ionize when they dissolve in water. They form hydrogen cations. They also form anions. Because acids form ions when they're dissolved in water, they are electrolytes. So what happens is you put this molecular compound into the water, and because it's an acid, the molecule is going to get actually pulled apart into ions by the water. So we group acids into two categories here, strong acids and weak acids. A strong acid ionizes completely. You put hydrochloric acid in water, it all ionizes. The hydrogen ions come off very easily, and you have no intact HCl molecules. With weak acids, though, only a small percentage will ionize, and most of them remain as molecules, and so there's only a few ions in a solution of a weak acid. So here are two examples of weak acids, hydrofluoric acid and acetic acid. And so here, instead of a single-headed arrow in the chemical equation, we write a double-headed arrow. That indicates that the reaction goes both ways. So we've got some of this, HF, intact molecules. We also have some hydrogen ions and fluoride ions. Here's a picture of an acetic acid solution. We see that a lot of it is intact molecules, but we do have some ions. So here's a hydrogen ion, and there's an acetate ion. Here's a hydrogen ion, and somewhere in here is an acetate ion. They're kind of hard to recognize. But a lot of it is the acetic acid molecules. So a weak acid ionizes weakly, a strong acid ionizes strongly. Yeah?
The
I do have a list. That's coming up. So strong electrolytes are substances that dissolve completely as ions. So that includes soluble ionic compounds and strong acids. Strong acids are strong electrolytes. These solutions conduct electricity well. You hook them up to a conductivity apparatus and the light bulb is very bright. It's a strong light. Weak electrolytes dissolve mostly as molecules, but partially as ions. So they make some ions, but not very much. So weak acids are weak electrolytes. These are going to conduct electricity, but only weakly. And so the conductivity apparatus, what you'll see is the light bulb lights, but it doesn't glow brightly. It glows weakly. So weak light, weak electrolyte, weak acid. Here's an illustration of that. So a non-electrolyte, like sugar, you put it in the water, nothing happens with the light bulb. A weak electrolyte, like acetic acid, you put that in the water, the light bulb glows a little bit. A strong electrolyte, like sodium chloride or one of the strong acids, you put that in the water, the light bulb's going to light up very brightly. Okay. I thought there was a slide here with the acids, but there doesn't seem to be, so I'll make one. So strong acids. It's probably coming up later, but whatever. So there are 6 strong acids, and you just have to memorize them. Sorry. HCl, HBr, HI. Those are the hydrohalides. So not fluorine. Fluorine's the little sister of that group, and that's a weak acid, but the others are strong acids. And then we've got perchloric acid and sulfuric acid and nitric acid. How do you know it's a strong acid? You memorize them. Sorry. There's 6 of them. It's not that bad. The weak acids, all the other acids. Now that's easy. So you memorize the 6 strong ones. Any other acid is a weak acid. Okay? Well, it won't be on the PowerPoint. Just go ahead and copy it down. Everybody got it? So let's talk about dissociation. When an acid is dissolved in water, acids are molecular compounds, so they ionize. They form ions that were not there before. When an ionic compound dissolves in water, it already had ions. So we don't say that it ionizes, but the ions will separate from each other. This is called dissociation. Association would be when things come together, right? Dissociation is when things separate. So we call this dissociation. So a soluble ionic compound will dissociate into the individual ions. If you have polyatomic ions in that compound, the polyatomic ion is going to stay together. So in this class, what we will see is that soluble ionic compounds always separate into 2 ions, 2 kinds of ions. One type of cation, one type of anion. We're never going to see 3 or 4 or 5. You can't separate the sulfur and the oxygen into individual ions. The sulfate ion stays together. Okay, so we got sodium sulfate, we get sodium ions and sulfate ions. This is sodium, what's my pointer? Sodium sulfide. So we learned when we looked at these formulas how to name them, we had to look at the ions involved. Sodium sulfide, because it has sodium ions and sulfide ions. So when those are dissolved in water, we just write the ions separately with their charges. So we've got an ionic solution, we've got separated ions floating around, we have a solution. But not all ionic compounds are soluble in water. We use the word soluble if a substance will dissolve in water, insoluble if it does not dissolve in water. Those are qualitative terms, and when you get kind of in between, then it's a little hard. Do you say this is insoluble or soluble? One thing that I want you to remember, and you'll learn more about this in Chem 1B, is that even an insoluble compound does dissolve to some extent. Maybe it's only a couple of ions that dissociate, but at least a couple of ions will dissociate. What we're interested here is, does a significant portion of the compound dissolve? Then it's soluble. If it's a very, very small amount, then we consider that to be insoluble. So silver nitrate dissolves in water. The ions dissociate. This conducts electricity. It's a strong electrolyte solution. Silver chloride is almost completely insoluble. You put silver chloride in water, you stir it up, and it just falls back to the bottom and it sits there, kind of like sand. It just, it's not going to dissolve. So the silver ions and the chloride ions do not separate. Why does this happen? Well, that's complicated. There are reasons, but it's complicated, and we don't have time to go to that complicated place. So there's several factors. It's not easy to predict. The best thing, the most straightforward thing, is called an empirical method by experiment. And so you take some of this compound and you put it in water and you see, does it dissolve? Okay, that one did. And you take another one and you dissolve it, see if it'll dissolve. Nope, that one doesn't. And then you just do this with a bunch of different compounds, and then you try to look for some patterns. Well, thankfully, we don't have to do that because people have done that for us. So these are solubility rules for ionic compounds in water. You can see there are different, if you look on the, I think it's the green cards have a solubility rules table. It's going to be slightly different. It might have some more things on it than this one, but this is the one that you need to be able to use, and you need to memorize it for a test, okay?
The whole thing?
The whole thing. I'm going to show you it's really not that horrible. So the table is dissolved into two sections. The top part is, these are compounds that are generally soluble. So if it has any of these ions in it, it's generally soluble. There are some exceptions, okay? The bottom is things that are generally insoluble. If it's got hydroxide in it, it's probably insoluble, except for these things. So all of this down here looks really awful, doesn't it? So what I encourage you to do is, so you've got a compound, you're trying to figure out if it's soluble or insoluble, start at the top and move your way down, and then we can ignore a whole bunch of these exceptions. So if it has lithium, sodium, potassium, or ammonium, it's soluble. You don't have to do anything else. These are the group 1 metals. So group 1A, the alkali metals. Alkali metal or ammonium, it's soluble. They're all soluble. Those are cations. If it has the anions, nitrate or acetate, those compounds are always soluble, no exceptions. Then we get to the halides, chloride, bromide, and iodide. Those are soluble except if you have these three ions, silver, mercury 1, or lead 2. Okay? So let's just simplify that. So the exception is if the cation, I want to cover that up. If the cation is one of these, then it's insoluble. Sulfate compounds, generally soluble, except with these guys. So again, let's get rid of the words. So if it's paired with one of these, it's also insoluble. Now notice lead-2 and silver are in both of these lists. The other three elements for sulfate are alkaline earth metals, group 2 metals. So here you've got those guys. I'm sorry, you just got to memorize those. And these guys. So if you get through that, you didn't have any of those ions. You're looking for hydroxide. Well, hydroxide compounds are generally insoluble, except, so this exception is when it has one of those. That's the first rule. If you saw lithium, sodium, potassium, or ammonium in that compound, you shouldn't even be looking down here. So we don't need to remember that. If we start at the top and move down, we'll never get to that point. Sulfide compounds are soluble with calcium, strontium, or barium. Those are strontium, barium, and calcium. Those were the same ones that were the exception up there. And for hydroxide, it's the same. The only thing that makes hydroxide is a little different is that instead of being soluble, these guys are only slightly soluble. But you know what? That's a detail that we could overlook and be okay with. So is that looking a little better? Then we've got carbonate and phosphate. Those are insoluble except with these ions. Well, again, that's the list at the top. If you had one of those, you shouldn't be looking at the rest of the list, so I'm going to cross that one off too. There. Is that better? Start at the top. If you've got one of these ions, it's soluble. Don't look any further. If you have to get all the way down here to phosphate, that means you didn't have one of these, and it's going to be insoluble. Okay? Predict whether each compound is soluble or insoluble. Nickel sulfide. Well, we've got two ions here. We've got nickel and we've got sulfide. Let's look at the table. So we start at the top and we work our way down. We're looking for nickel or sulfide. We don't find anything up there. Here we've got sulfide, that S2 minus. So that's generally insoluble. And then we need to look over here. Is nickel one of the exceptions? Nope. So that tells us that this one is insoluble. I'm trying to write with a white marker. That doesn't work very well. Nickel sulfide will not significantly dissolve in water. Magnesium phosphate. I hear insoluble. So we go through here. We're looking for magnesium or phosphate, and we don't find anything. We did on here to phosphate. Phosphate's insoluble. So this is insoluble. The ones in the bottom half are insoluble with the stated exceptions. The ones in the top are soluble, and the exceptions are insoluble. So lithium carbonate, soluble because lithium. Lithium, sodium, potassium, or ammonium, it's soluble. Doesn't matter what the other ion is. So that's soluble. What's this guy? That's soluble too. It starts with NH4. Yeah, question?
When it's soluble, it's also aqueous too, right?
Yeah, so if you come across this in a chemical equation where there is water present, you would write AQ after it because it dissolves. If it's something that's insoluble, even if it's in water, you would give the state as solid because it does not dissolve. Any questions?